Okay, this is going to be a short video about using Circuit Maker to perform Fourier analysis. It's a tool that's available with Circuit Maker. Here we have a very simple circuit with a sine wave generator. Looks like 1 kilohertz, 2 volts peak to peak, being loaded by a 1 k ohm resistor. And let's run this. And we see this result. We're very familiar with the bottom right oscilloscope display, which shows us the 1 kilohertz sine wave. We could put our cursors on that, but I have all the screenshots on a Word document available that you can blow up and see this for yourself. The top display is called Fourier Analysis, and we may recall that Joseph Fourier was a mathematician, and in the 1800s he came up with a mathematical way of dealing with heat transfer. We have since adapted that to deal with signals, and we can actually take any periodic signal and just mathematically model it as a infinite series of sines and cosines and harmonics of the fundamental frequency of the periodic waveform. In the case we see here, it turns out that the sine wave is just a pure sine wave at 1 kilohertz. And if we take a look, and let's blow up the Fourier analysis, and what we see is across the left hand scale we have a voltage. 1.2 volts is the top, and 1 volt is the peak of the green spike. It turns out the green spike is located, as we could grab a hold of cursor A here and bring it down and discover that it is located at 1 kilohertz. You can see that up in the top X sub A in the top left hand corner. So what the Fourier analysis tool does is displays what frequencies are in a signal, and here we had a 1 kilohertz sine wave, so there's only one frequency, the 1 kilohertz signal. Now in real life, if we had a signal generator, we would discover there are harmonics. Of course, this is simulation, and it turns out the simulation has suppressed those harmonics right now. If we put the scale, the horizontal scale, to dB, we would see those harmonics, but I'm not going to do that right now. Let's stop this, and just so you understand what's going on here, I'm going to take and click on this guy here, right click it, edit the device data, and change it to, oh, this is the wrong one. I want to edit the device, the edit signal generator, and let's change it to say 4 kilohertz. So I just take and put in a 4 here and hit OK and run it, and what you observe is, get rid of this guy, that what's happened is that the spike, which represents the signal, has now moved over to 4 kilohertz. And if we were to change it again, here I'll run the cursor over, and the cursor, you can see up here, says 4 kilohertz. Now, anytime I would change that signal generator output, the spike would move around the screen. Right now the screen is set up to go from 0 to 9 kilohertz. It's limited by the simulation setup that I did, so I won't take in, well, let's do one more. Let's go and say we want to set this to say 6 kilohertz. So if I take in, edit the signal generator, get the right one this time, and backspace. Oops. Put a dot in there. 6 kilohertz. Hit OK. run this, and sure enough what's happened is the spike has moved over to 6 kilohertz. So the Fourier analysis allows you to see what frequencies are in the signal. And of course it's just a sine wave, so nothing exciting. So I'm going to stop that. I'm going to go and load up my next circuit. And this one shows, I'll blow it up a little bit. Let's make it 150. And move it up in the screen. Okay, so what I have here, as you can see, is a 1 kilohertz, a 5 kilohertz, and a 10 kilohertz signal. So let's take and run this. And we'll see both the time display and the frequency domain versions. So if I take a look at, let's blow this guy up, what I see in an oscilloscope. Now you may have seen this in a television show or a movie someplace where maybe somebody's talking into a microphone and there's a microphone active, and on an oscilloscope display you see somebody speaking. Here you see the combination of the 1, 5, and 10 kilohertz signal, but they're kind of jumbled up. A trained eye can point out the fact that, well, okay, from here to here looks like one of the frequencies, from here to here looks like another one of the frequencies, and you know, who knows? I mean, it turns out that it's very difficult to ascertain what frequencies are really in the signal. So you might just be aware of the fact that if I have voice or music, there's many more frequencies, and hence it's very difficult to ascertain what frequencies are in the signal. Now, we'll take and make this one go smaller, and let's take a look at the Fourier analysis, and sure enough, here we see a distinct display that shows a signal down here at 1 kilohertz, one at 5 kilohertz, and one at 10 kilohertz. So the use of the spectrum analyzer or Fourier analysis is the fact that we can see very discrete signals in the presence of other signals, whereas with the oscilloscope it's not so easy to ascertain what's actually on the oscilloscope displays. I'll go back to this guy. So again, it turns out we can actually see exactly what's there with the spectrum analyzer. And not shown here, but we can see small signals in the presence of large ones. We cannot do that. The dynamic range of an oscilloscope or the time domain display is too small for that. Or rather, is not very good for seeing that. Now, I'm going to go to the middle one here, and I'm going to edit this guy, and I'm going to go set my peak amplitude to 0 and hit OK. So what I've effectively done is gotten rid of that middle signal generator. By the way, a signal generator with 0 output is considered to be a short. So if I run this now, what we see is these two distinct displays. Let's take a look at the top one first. And again, here we see very distinctly the 1 kilohertz on the left hand side and the 10 kilohertz in the middle. So it's very obvious what frequencies are in that signal. Now we've added these signals together. I'm going to take and get rid of this guy, I hope, and bring up this guy, the time domain. And now this one, it turns out that you can really see the two frequencies there. The sine waves, which happen very rapidly, these guys here, from here to here for instance, is the 10 kilohertz signal, and we can see the much lower 1 kilohertz or 10 times lower in frequency signal here. And so it's not too difficult to ascertain what frequencies are in this signal. Again, if I went from tip here to tip over here, I would find I'd have 1 kilohertz. And if I go from tip here to tip here, I'd have 10 kilohertz. So we can see, and you know, of course, maybe our eyes are a little better trained since we, you know, play with oscilloscopes and see sine waves, that here, indeed, it turns out it's easy to see these two signals added together. But if we have more than two, it's not as easy. Okay, so now I'm going to go back to the first one, I believe. Let's see. Do I want to do that? File. Yes, I want to go back to the first one. And here we go, Fourier analysis. Now what I'm going to do is I can take and change what this signal generator puts out. So I'm going to take and blow it up again. Do the display scale, make it 200. And move it up in the screen. So what I'm going to do is right click it, edit the signal generator, and I'm going to change it to a different type of wave. I'm going to make it into a pulse waveform, and I'm going to change its period from 1 microsecond to 1 millisecond. I'm going to change the pulse width to microseconds here. I'm going to hit OK. And one last thing, let's take and change its initial amplitude to minus 2.5 volts, and go up to not 5, but let's go up to 2.5. So I'll take this guy here and make that 0.5 and make this 2. So now it goes from minus 2.5 to plus 2.5, and it's got a 1000 hertz frequency. So this is a square wave now, or a pulse. You'll see that in a second. Let me just run it for you, and let's concentrate in the bottom one. So this is one we're more familiar with. So here we have this square wave, and you can see it goes from minus 2.5 up to plus 2.5, or 5 volts peak to peak. And I get 1000 of these per second, so we'll say its pulse repetition frequency is 1000 hertz, or its fundamental frequency is 1000 hertz. I could lay a sine wave on top of this, and the sine wave would take and go and peak here and go down to 0 and go down to minus peak and so forth. So it turns out the fundamental frequency is 1000 hertz. Now, that's what we like to see in the time display of the oscilloscope. And you know, I could take and create the signal by taking and flipping a switch. If I was real good, I could take and switch back and forth very accurately if I was real good at it, like a metrodome, and you know, have maybe a 2.5 volt battery and a minus 2.5 volt battery, and create the signal mechanically. Let's take a look at what this is on the Fourier analysis. On the Fourier analysis, we see that we have what? The one, let's take and grab A here, grab the cursor, and we go all the way over, and we discover here we have the 1 kilohertz signal, and let me make that up here, 1 kilohertz. And then we have another signal over here, so let's grab B, and if I grab B, what happens when I put that cursor on it? Oops, I got to be real careful here. I go over right about here, I think. And if we take a look at B, we'll see it's 3 kilohertz. So I've got the odd harmonic, the third harmonic of the fundamental 1 kilohertz. And also notice to its right, I have a signal at 5 kilohertz, and one at 7 kilohertz, and I have a little bit of a signal at 9 kilohertz. So let's take a look at the relative amplitudes of these things. So if I go with my cursor C here and bring it down, it looks like I have a signal of about 3.2 volts. I did it real fast. 3.2 volts for the fundamental. I'll take D and bring it down here, and I've got somewhere close to 1.032 volts. Now, in the screenshots, I've taken and done this exactly for you, so you can see all the measurements. But you would see that roughly the fundamental is 3 times the amplitude of that third harmonic. As a matter of fact, you could Google this, you'd discover that for a square wave, the amplitude of the various harmonics go down by a factor of 1 over n, where n is the harmonic. So it turns out that mathematically that's what Fourier series would show, that a square wave consists of odd harmonics of the fundamental, and they go down, the amplitude goes down by 1 over n, which means their power would go down by 1 over n squared. And you may have a problem wrapping your head around this, but it turns out that, sure enough, let me go back, here's the square wave, and we mentioned before that, I I could do this mechanically. Well, this would be the basis of a mechanical oscillator. It turns out the physical action of throwing a switch back and forth like a metronome to produce a signal would actually produce these new frequencies that you see on the Fourier analysis. You know, in your life experience, you may be aware of the fact that when we have a thunderstorm, you have lightning, and lightning is a little bit different. It's like an impulse, and it turns out that impulse generates all frequencies whose amplitude goes down by 1 over f, actually. And it turns out that we could use a Fourier transform to actually predict that. Here with this repetitious waveform, it turns out we have odd harmonics. And again, the screenshots, I go and measure all these things fairly accurately, the amplitudes, and so you can see how they go down and compare them versus the 1 over n formula I just mentioned. Okay, so I'm going to stop that guy. Then I'm going to go and load the last waveform. This is circuit number 3. Here's circuit number 3. I'm going to open this up. I don't want to save that. And let's take and blow it up a little bit. Let's view. This time we can probably go 200. And let's see, bring it around a little bit into the center of the screen, a little bit more. Now, let's take a look at the signal generator. In Circuit Maker, we make piecewise signals. That is, it looks like the Alps or a mountain range or something there inside that signal generator. You'll see what it is actually in a second. Let's take and run it. And if I run it, it turns out that it's this waveform here, a triangular waveform. So I can make that by a piecewise in simulation world, and it turns out that it repeats over and over again. So here's this sawtooth waveform, and let's take a look what we see when we take a look at the Fourier analysis of it. In the Fourier analysis, lo and behold, we see the fundamental. This time it's at 2 kilohertz, and again the screenshots will show you this. So this guy here, if I bring over cursor B, this guy here is at 2 kilohertz, and it turns out that this guy here, I'll bring over A now this time, and this guy here is going to be at 6 kilohertz. And it turns out that the fundamental frequency is 2 kilohertz, the third harmonic would be at 6 kilohertz, and the next one over here would be at, let's see, 10 kilohertz because it's a fifth harmonic. This guy would be 14 kilohertz, it's a seventh harmonic. There's a little one there, you can't see it very well. Of course, if I take and go and go to manual here and blow these guys up, you can see them a little bit better. So it turns out that I still get, for the sawtooth wave, I get odd harmonics, but their amplitude goes down a lot faster. Actually, mathematically, if you did Fourier analysis, you'd discover the amplitude goes down by 1 over n squared now. So for the third harmonic, the amplitude should be down by 1/9. The fifth harmonic should be 1/25. The seventh should be 1/49, and so on. And I do that with the screenshots for this experiment. Okay, so I'm going to stop that guy. Now, what I'm going to do is some advanced Fourier here, which is not in the screenshots, but let's take a look at what I've got here. So advanced Fourier analysis number 1. I want to save that. In the interest of time, I don't think I'll blow this guy up. This basically looks like the same thing we just had. It turns out that, lo and behold, yeah, here's a it's a square wave. This time it just goes from 0 to plus 8 volts and back down to 0. So it's a unipolar square wave as opposed to the bipolar one I had before. That probably shouldn't make too much difference. Then we'll go and take a look at the Fourier analysis. From the Fourier analysis, I've changed the scales here. I actually go all the way to 60 kilohertz. The fundamental here, I think, is still a 1 kilohertz signal. So there's 1. The next one here is 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25, 27, 29, and you can't see past that. So the 29th harmonic is the last one. We did mention that Fourier analysis, what it does is allow you to represent any periodic signal as an infinite series. Of course, after a while, when you get up to very high harmonics, it turns out the amplitude of those harmonics are extremely small at that time. So here's again, a square wave. What we don't want to really show that. What we want to do is take and go and load up the next file. Let's take a look at the next one, which is number 2. And I'm going to hit open here. And again, for interest of time, I won't blow it up this time. I'm going to run it. And in this case, what we see is I've taken and changed the duty cycle. No longer is the duty cycle 50%, that is 50% on and 50% off. I'm guessing here the duty cycle looks like it might be about 25%. And it turns out that now what happens is when we take a look at the Fourier analysis, what happens, we tend to get groupings. And it turns out that we have both odd and even harmonics, and it looks like some are even missing. So this is the 1 kilohertz, 2 kilohertz, 3 kilohertz. What's missing is 4, here's 5, 6, 7. What's missing is 8, 9, and 10 kilohertz. So we're missing the 4th and the 8th harmonic because of the duty cycle. And let's close this one out and grab the next file and see how this progresses. So here we go with advanced analysis number 3. Let's see what we have here. I'm going to open it up, and again, interest of time, I'm not going to take and expand. I'm just going to run it. And lo and behold, we can see that now the duty cycle might be like 10%. And what happens? Lo and behold, the Fourier analysis ends up like this. So here we're missing the harmonic at 10 kilohertz, at 20 kilohertz, 30 kilohertz, and so forth. But we see we have in between there quite a few other ones, and they're starting to take on a shape. Actually, the pulses here are taking on the shape of a sync pulse, which is a sine of x over x. Let's take and open up the next one, where we probably have taken and lowered the duty cycle even down further. But before we get to the extreme, let's take a look at this guy, and we run him, and now again you can see that maybe I got like a 2% duty cycle on these pulses. But let's take a look. The more interesting thing is the Fourier analysis. The harmonics are getting closer and closer, and it looks like we actually have not even harmonics but subharmonics, and you can see a distinctive shape to these blips here. I'm going to get rid of that guy, and I'm going to go to the last one, and now what I've got is a periodic bunch of impulses. That is, I've got very short pulses, like again lightning strikes or lightning bolts. And let's take a look at what happens with this guy. I'll open this guy up. We don't want to save anything, and we'll open them up, and let's see what we have. So these very, very narrow pulses, which are like impulses, and they're periodic. And what do I get? This guy here is almost totally filled in. In other words, the frequencies are getting closer and closer together, almost like a continuous amount of energy put out at a big range of frequencies, but in a shape of a sync pulse. So if you learn Fourier analysis and Fourier transforms, you could take and mathematically calculate these things and plot them. This circuit maker simulation program does that for you. And again, if we use the spectrum analyzer, which is a radio receiver, we could see the same thing. So that's it for this experiment.